Long short-term memory networks, commonly known as LSTMs, were introduced to solve a very specific and stubborn problem that emerged when training recurrent neural networks on long sequences. Early recurrent models were elegant in theory but fragile in practice. They struggled to learn dependencies that span many time steps because gradients either shrank toward zero or exploded during backpropagation through time. LSTMs represent a carefully engineered modification of the recurrent architecture that allows information and gradients to flow across long temporal distances with much greater stability. To understand why LSTMs were necessary, it helps to briefly recall how a standard recurrent neural network operates. In a vanilla RNN, the hidden state at each time step is computed by applying a nonlinear transformation to the previous hidden state and the current input. The same weight matrix is reused at every time step. When we unroll this computation across a long sequence and apply backpropagation, the gradients must pass through many repeated multiplications by the recurrent weight matrix and activation derivatives. Unless those transformations are perfectly conditioned, the gradient norm will tend to either decay exponentially or grow exponentially. This makes learning long-term dependencies extremely difficult. The LSTM architecture introduces a memory cell and a set of gating mechanisms that regulate information flow. The central design goal is to create a path through time where gradients can propagate without vanishing. Instead of forcing the hidden state to both store and transform information in a single vector, LSTMs separate the persistent memory from the transient hidden representation. This separation is the key conceptual innovation. At the heart of an LSTM is the cell state, often denoted as C_T. You can think of this as the long-term memory of the network. Unlike the hidden state in a vanilla RNN, the cell state is updated primarily through additive interactions rather than purely multiplicative ones. Additive updates are much more gradient-friendly because they allow error signals to flow backward without being repeatedly scaled by small factors. Surrounding the cell state are three gates: the forget gate, the input gate, and the output gate. Each gate is implemented as a small neural network layer with a sigmoid activation that produces values between 0 and 1. These values act as soft control signals that determine how much information passes through. The forget gate decides how much of the previous cell state should be retained. This is crucial because not all past information remains relevant forever. The forget gate looks at the current input and the previous hidden state and produces a vector of retention coefficients. If a component of the forget gate output is close to 1, the corresponding memory is preserved. If it is close to 0, that portion of memory is erased. This mechanism allows the network to learn when to intentionally forget stale information. The input gate controls how much new information should be written into the cell state. It works together with a candidate memory vector that represents potential new content. The input gate scales this candidate before it is added into the cell state. This selective writing prevents the memory from being overwhelmed by noise at every time step. The output gate determines what part of the cell state becomes visible as the hidden state at the current time step. The hidden state is typically what downstream layers see. By filtering the exposed information, the output gate allows the internal memory to remain rich while only revealing the components relevant for immediate prediction. One of the most important mathematical properties of the LSTM is the linear path through the cell state across time. If the forget gate remains near 1 and the input gate near 0, the cell state can persist almost unchanged across many time steps. During backpropagation, gradients can flow along this path with minimal attenuation. This is sometimes described as the constant error carousel, though the modern view is more nuanced. Training LSTM still uses backpropagation through time, but the gating structure dramatically improves gradient conditioning. In practice, LSTMs can capture dependencies spanning hundreds of time steps, which was very difficult for early vanilla RNNs. From an implementation perspective, each LSTM cell performs several matrix multiplications at every time step. The gates and candidate memory are typically computed in a single combine-defined transformation for efficiency, then split into separate vectors. This fused computation is important for performance on modern hardware. The dimensionality of the hidden state and cell state is a key hyperparameter. Larger states increase representational capacity but also increase computational cost and overfitting risk. In many applications, practitioners experiment with hidden sizes ranging from tens to thousands of units depending on dataset scale. Another design choice is whether to use a single LSTM layer or stack multiple layers. Deep LSTM stacks can learn hierarchical temporal representations, where lower layers capture short-term patterns and higher layers capture more abstract or longer-range dependencies. However, deeper stacks increase training difficulty and latency. Bidirectional LSTMs are widely used when full sequence context is available. In this setup, one LSTM processes the sequence forward in time while another processes it backward. Their hidden states are concatenated or combined. This allows the model to incorporate both past and future context when making predictions. Bidirectional LSTMs have been especially effective in tasks like named entity recognition and speech processing. In sequence generation tasks, LSTMs are often used in encoder-decoder architectures. The encoder LSTM processes an input sequence and compresses it into a context vector, which initializes the decoder LSTM that generates the output sequence. This architecture was foundational in early neural machine translation systems. However, the fixed-size context vector in early encoder-decoder models created a bottleneck for long sequences. Attention mechanisms were later introduced to allow the decoder to dynamically access different parts of the encoder's hidden states. This was a major step forward and eventually led to the dominance of transformer architectures, but LSTMs with attention remained competitive for many years. Regularization in LSTMs requires care. Standard dropout applied independently at each time step can destabilize the memory dynamics. Variational dropout, where the same dropout mask is applied across time, is often preferred. Recurrent dropout variants selectively apply noise to the candidate memory while preserving stable gradient flow through the cell state. Gradient clipping is still commonly used when training LSTMs because exploding gradients can still occur, especially in deep or poorly initialized models. Clipping by global norm is a standard defensive technique. Initialization of LSTM parameters can significantly affect training speed and stability. A common heuristic is to initialize the forget gate bias to a positive value, often around 1.
The question is,
this encourages the network to initially retain memory rather than immediately forgetting, which empirically improves learning of long-term dependencies. From a computational perspective, LSTMs are more expensive per time step than vanilla RNNs because of the gating computations. They also remain inherently sequential across time, which limits parallelization. Each time step must wait for the previous hidden state. This sequential dependency became a major bottleneck as datasets and models grew larger. Despite this limitation, LSTMs were the dominant sequence modeling architecture for many years. They powered advances in speech recognition, handwriting generation, language modeling, machine translation, and time series forecasting. Their ability to maintain long-term context made them dramatically more effective than earlier recurrent models. It is important to understand, however, that LSTMs do not magically solve all long-range dependency problems. Very long sequences can still be challenging, especially when relevant information must be precisely retrieved after many time steps. The memory in an LSTM is distributed and continuous, not an explicit symbolic storage system. Retrieval fidelity can degrade as more information accumulates. Another subtle limitation is that the memory capacity of an LSTM is bounded by the dimensionality of its cell state. If too much information must be stored simultaneously, interference can occur. This is one reason attention mechanisms and external memory architectures later gained interest. In modern practice, transformers have largely replaced LSTMs in large-scale natural language processing because attention allows direct interaction between distant tokens and enables full parallelization. However, LSTMs remain highly relevant in certain domains. In low-latency streaming applications, their constant memory footprint and causal structure are advantageous. In smaller datasets, their strong inductive bias toward sequential continuity can still outperform larger attention models. For time series forecasting, especially in industrial settings, LSTMs are still widely used. Their gating structure handles seasonality, trends, and temporal noise reasonably well when properly tuned. They are also common in embedded and edge deployments where model size and compute must be tightly controlled. From a theoretical viewpoint, LSTMs can be interpreted as learned adaptive filters over time. The forget gate controls the effective time constant of memory decay. The input gate controls the strength of new signal injection. The output gate controls exposure of internal state. Thinking in signal processing terms can provide useful intuition for hyperparameter tuning and failure analysis. When diagnosing LSTM models, practitioners often examine gate activations to understand whether the network is using its memory effectively. If forget gates saturate near zero, the model may be discarding context too aggressively. If they saturate near 1, the model may be accumulating stale information. Monitoring these dynamics can provide insight beyond simple loss curves. In summary, long short-term memory networks represent a carefully engineered solution to the gradient flow problems that limited early recurrent neural networks. By introducing gated control over a persistent memory cell, LSTMs enable stable learning over much longer temporal horizons. They embody a powerful design principle in deep learning. When optimization difficulties arise from architectural constraints, modifying the information pathways can be more effective than simply changing the optimizer. Even as newer architectures dominate some benchmarks, the conceptual contributions of LSTMs remain foundational. They taught the field how to think about memory, gating, and gradient preservation in sequential models. For anyone working deeply in AI systems, understanding LSTMs is not just about historical knowledge, it provides enduring insight into how to design neural architectures that can remember, forget, and reason across time.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.